So hello everyone. Welcome to the live section of this course, which is on Foundation of Classical Electrodynamics. So I'm Gitanjali. I'm a PMR scholar from IIT Delhi, and I'm the TA for this course. And we are now approaching towards the end of this course, I think we are in week 12, which is the last lecture complete of this course. So I will briefly discuss about whatever the concept that has been taught in week 12, and we'll try to solve few problems that is related to uh, the weekly content. So I hope my voice and the screen is visible to you. If not, let me know so that I can make it correct in the meantime. Okay, if it is fine, then let us start. So for week 12, we basically see what are the Maxwell's equation in different medium. It can be conducting medium like a metal, or it can be a dielectric medium, or it can be a lossless or a vacuum. So to solve the Maxwell's equation, for a general Maxwell's equation, to solve it, what we did, we can use two types of Gauss condition. One is the Lorentz Gauss, and other is the Coulomb Gauss. So if you recall Coulomb Gauss, it is given by divergence of A is 0, and the Lorentz Gauss, it is given by divergence of A is 1 by c square minus 1 by c square dou phi by dou t. So A and phi are these are the vector and scalar potential related to the physical fields that we are studying. So if even though if the given vector potential it is not satisfying this Lorentz Gauss and Coulomb Gauss condition, we can make a transformation of this vector potential. So we can take a new vector potential, which is given by A is given by A plus some gradient of some function phi t, and simultaneously we have to make a transformation of the scalar potential phi, which is phi minus dou phi by dou t, dou phi by dou t. So we can make this transformation. In this transformation, they doesn't change the physical fields that we want to study, which is electric and the magnetic field. After that, we've seen what is the solution for Maxwell's equation in free space. So in free space, there is no source charge. So charge density is 0, and current density, displacement current, these are all 0. So you can simplify the Maxwell's equation further. So divergence of B, it's 0. Divergence of B is also 0. Curl of E, this is minus dou B by dou T, and curl of B is mu naught epsilon naught dou E by dou T. And when you take the curl of this third equation and do some mathematical simplification, so you see that we can get a wave equation for the electromagnetic field in vacuum. So this is given by divergence square del square minus 1 by c square dou square E by dou T square. It's 0. So this is the wave equation that we see in the that we have in the vacuum. And the solution for this is the plane wave solution. So you can write E RT as some E0 e to power I k dot R minus omega t. Similarly, we can have the magnetic field as also a plane wave solution, and this can be given by BRT is B0 e to power I T dot R minus omega T. These are the plane wave solution in the vacuum. And you can also, if you use this solution and simplify this for Maxwell's equation, you can see that you can write del dots as ik dot or del cross is ik cross and dou by dou t is minus I omega. So you can use this simplification, then you notice that if you use this, then you find that the k vector, which is the propagation vector, it is perpendicular to both E and also perpendicular to B. So these are all mutually perpendicular and we call it as a transverse electromagnetic wave. And for this transverse electromagnetic wave, you can also find out what is the energy density. If you recall, it can for the electric field, the energy density you can get it by taking the integration of half epsilon naught E square dV. And for magnetic field, it is 1 by 2 mu naught B square dV. And total will be the summation of the whole term, both the magnetic and the electric field energy density. After that, we saw one of the most important parameter which defines the flow of energy for a electromagnetic wave. So this is the Poynting vector, which is nothing but the energy flowing per unit area per unit time, or indirectly it defines the intensity of the electromagnetic wave. So this by definition it is E cross H, or you can write it as E cross P by mu naught for the vacuum condition. Or in general case, so you can write it as mu, the permeability of the medium. And using this, you calculate what will be the average energy flowing per unit area per unit time, and it comes out as half epsilon naught C E square or E naught square. This is when you put this plane wave solution and do some the mathematical simplification, you get this. And after that, you also see what is the Maxwell's equation for a medium. For a medium, it can be the charges will be there, so you can use divergence of D is rho f, divergence of B is 0, and curl of A is minus rho B by dou t, and curl of S J external plus dou D by dou t. So these are the general equation, and when when the wave travels from one medium to another medium, like the wave is incidenting from free space on a metal. So for the in the boundary, the continuity should hold. And using the condition for the Maxwell's equation, we found that the perpendicular component of B is continuous, and the parallel component of E is continuous, and the D perpendicularity is discontinuous, and the discontinuity is given by the charge, surface charge, and also the parallel component of this magnetic field. It is also discontinuous and it is given by K cross L. Okay. And using this, you also see what is the expression for the electric field and magnetic field in a metal. So for a metal, you can will solve a problem that the electric field and magnetic field they lag with each other. It's like in vacuum they are in phase, but when you consider a absorbing medium, there will be out of phase condition. Okay. So this is all briefly what we have seen in week 12. So let us start solving the problems. The first question is quite trivial. So this is only for you to let you to recall what the concept has been taught in the class. So go through the question and let me know the answer. So it's quite straightforward. So there is a two types of vector and scalar potential is given. One is VA and one is V prime A prime. Denote two sets of scalar potential and vector potential. And psi is a scalar function. Then you need to find out which one of the following transformation leave the electric and magnetic field and hence the Maxwell's equation unchanged. So there are four options. Let me know the what is the solution for this. Good. So this is option A. So it's quite straightforward. Let's see question number 2. So it will take some time to calculate it. So let me solve it in detail. So there is a current carrying Y which is created by a narrow beam of protons moving in vacuum with constant velocity u. The direction and the magnitude respectively of the Poynting vector outside the beam at a radial direction, which is much larger than the width of the beam from the axis R. So we need to find out the Poynting vector outside the current carrying wire at a radial distance R, which is much larger than the width of this beam. Okay, so uh, even though it's not a electrostatic case, so in electrostatic case we consider that the source charge should be at rest. Like for Poynting vector, what we need? We need the electric field and the magnetic field. Magnetic field, it's easy to find out because it's a long current carrying wire, so it is nothing but mu naught I by 2 pi r. But here you can see the proton is moving. So you may think that we can't use the electrostatic case, but when the velocity is much, it's not given whether it is traveling at the higher velocity, which is much larger than the speed of light. Generally, it's not the case. All the particles move at a much smaller. In non-relativistic case, it's much smaller than the speed of light. So we can consider the electrostatic electric field here. So for that, let us say we have lambda charge per unit length, which is the number of protons per unit length. So for this lambda charge, what will be the current? I is nothing but dq by dt, right? So you can write it as lambda into u. U is the speed of this proton. So lambda u will give the current of this proton beam. So that means you can get lambda is I by u. So can anyone know, let me know whether my voice is audible because I think I'm speaking in low voice. Okay, so we have lambda is I by u. And for this lambda, so whenever you have a lambda charge distribution, the electric field, you can write it as, you can use the Gauss law to find out the electric field. So you can take a current loop. Sorry, you can take a Gaussian surface, which is for these, it's like it will be a cylindrical one, right? And the electric field is in the radial direction, and you have to take the surface area of this cylindrical portion, which is 2 pi r. So electric field will be lambda by 2 pi epsilon r. This I hope you know the detailed calculation of this electric field. If not, let me know. So after that, you can make a substitution because here you can see the answer is given in terms of I and U. So you need to change lambda from lambda to I and U. So this is I by 2 pi epsilon UR RK. So this is the electric field For magnetic field, so this is mu naught I by 2 pi r. So pointing vector is, so let us use this equation. So this will be mu naught pi square 4 pi square sin mu r square. And the direction will be, this is r cap phi cap. So this r phi will give minus j, I think, plus it. So okay, so we need to eliminate mu naught also. So for this, what we can do, so C is there, I think. Mu naught will cancel. Okay, there will be one mu naught here, so which will cancel with the. So this is I square by pi square epsilon mu r square z cap. 4 will be there. Okay, so this will be our answer, and let us see which one is that. So option C. This is the correct answer. So is this clear? Okay. So let us see our next problem. So we have a electric field of a plane electromagnetic wave propagating in the vacuum. It is E0 x cap minus Iy cap to the power I Pz minus it. Find the time average Poynting vector. So in vacuum we can write curl of so curl of E is minus dou B by dou T, right? And if you do the simplification, then you will get K cross E is omega B. This you should know. So that means B is K cross E by omega. So we need to find out K, and omega is there. Let us first calculate K. So anyone can anyone tell me what will be K? K vector is Z cap. But I think what about is K is it's nothing but the coefficient of the position coordinate. So it is in Z direction, so unit vector will be in Z direction, but the magnitude will be K. So K vector in total is K Z K cross E. It is not KZK cross E is escape minus IYK 8 power I kz minus omega t. So we have E0k. Just take the cross product of z with x and y. You will get it is y cap and plus ix cap e to power I kz minus omega t. So that means h is a naught k omega mu naught y cap plus ix cap e to power I kz minus omega t. So we know the magnetic field now. So we can easily calculate what will be the average value of Poynting vector. And if we recall for a vacuum, it is average value is. So this is one of the expression that you can use. This you can. Sorry, give me a minute. I will take water. So in class, I think you can recall it is half epsilon naught C E square, naught square. So this is for the case where we have the plate wave solution. But another expression that you can use to get the answer for this is so here it's like there is a phase factor is also here. So for this, what you can do, you can use this relation A cross S star or so this is similar to what we have seen in the class, but it was not explicitly shown. Or A star H. So we have E and H. So let us see. So this is real. This is E0K omega mu naught. Uh, let us take this one. So E we have x cap minus I k cross y cap minus ix cap. And the exponential part, this will cancel with this one. When you take the star, this will cancel. So we have this. So let us simplify it. So half V0K by omega mu naught, real part. So when you solve it, this you will get 2z. That means this will be V0 C by mu naught z or A0 square epsilon naught by mu naught. Okay. Check it whether the solutions are okay with you or not, or you have any doubt. Let me know. Is it fine? Answer, I think it will be B. Let me connect my tab. It got disconnected. I don't know how. Why. In the next question, we have question number 4. Which one of the following is true for a plane wave of angular frequency omega and the propagation vector k? Propagating vector is in the free space. So this is conceptual one. I think you know the answer. Sorry, it's happening. Give me 1 minute. Answer is, I think, option A. Yes, it's correct. Okay, so answer is option A. Okay, next, let us move to our next problem. So in question number 5, find the skin depth of a gold conductor at frequency 1 gigahertz with conductivity sigma 4.55 into 10 to the 7 Simon per meter. So I think it's also quite easy. You just need to know what is the expression for the finding out the skin depth. Anyone recall what is the answer for this? What was the expression and how we can find the answer for this? So skin depth, it is delta is 1 by square root pi f mu naught sigma. So this is 1 by root pi. F is given 1 gigahertz, which is 10 to 19. Mu naught is 4 pi into 10 to -7. And sigma is already given. It is 4.55 into 10 to 7. So this is approximately will get 2.36 micrometer. Okay. So answer will be option C. For question number 6, there is a electromagnetic wave propagating in a non-magnetic medium with a relative permittivity epsilon is 4. The magnetic field for this wave is, it's given H X Y is AK X0 cos omega t minus alpha x minus alpha root 3y. X0 is a constant. It's not a function of x and y. So for this expression, field expression, you need to find out what is the electric field. So if you recall the Maxwell's fourth equation, which is modified Ampere's Maxwell equation. So it is given by curl of H is dou d by dou t, right? So even though you don't know the direct relation between H and the direct simplified relation, you can easily find out if you know the Maxwell's equation correctly. So you know that for a plane wave, it can be del can be written as I cross ik, and the dou by dou t can be written as minus of I omega. So this is for the case when we have e to power I k dot r minus omega t type of expression. But when it is opposite, like omega t minus kr, so dou by dou t will be I omega and del will be minus ik. Okay. So for this case, you can see this is omega t minus kx. So, but the relation won't change. Only the one negative sign will go from left side to right side. So this doesn't matter actually. If you although take this type of relation, the final relation will be the same. So this you can write it as I p cross h and dou by dou t of this dou by dou t is I omega and d is epsilon p. That means E is P cross H by omega epsilon. P. So this you can write it as B. For a medium, it is B. For in free space or in vacuum, it is C. So let us see what is K here. So K is nothing but the coefficient of X, Y, or the position coordinates. One is alpha and one is alpha root 3. Alpha is for X and alpha root 3 is for Y. So K vector, you can write it as alpha ik plus alpha root 3 jk. So that means KK is K by mod K. Mod K, this will give 2 alpha, right? So this is K. Now we can find out what is the electric place. So let us see K cross H. It is half cycle, or let us calculate the final expression. Is 1 by 2 V epsilon K cross H. 1 by 2 V epsilon I K root 3 J K. K is 0 cos omega t minus alpha x minus alpha root 3 by. Can you please calculate it and let me know the final answer? Which one of these following option will be correct? Sorry. It is option A actually. Or okay, so this is the electric field. So we need to do the simplification for 1 by V epsilon, right? Hmm, this is the minute. C is there, so I think we need to. So epsilon, this you can write it as and this is mu naught by 2, 1 by square root epsilon mu naught is C, and 1 by epsilon r is given, it is 4. So we will get 1 by 4 mu naught C, yes, mu naught C by 4. Okay, so let us see. I think there is, this is I cap and J cap, and this is K cap. So my K plus J cap, so I'm just looking at the unit vector. So this is in K cap. I K will give minus J, right? This minus, and JK will give I. So I minus root 3. Where is I minus root 3? I minus root 3 J. Magnitude, is there any problem? Root 3 I minus root should be. I will minus J. Okay, so there is a problem here. So this is half, sorry for the half IK plus root 3 by 2 JK. K cross H is in the KK direction. So IK will give minus I, sorry, minus J. Minus JK, half we have already taken it out, plus root 3, JK will give I. So root 3 I minus J. Okay, option C, not option A, but C. I think earlier it was, let's say, the expression was not quite correct. So now I think, I hope we will get it. So this will be the final expression for the electric field. Okay. Oh, is it fine, or if you want to, I can solve it again. So it's like we have H, then we have calculated what will be the expression with E with H, which is E is KK H cross H by V epsilon. Then we find out what is K, then unit vector, and we put it, and we have simplified 1 by V epsilon. Okay. Let's wait for 2 minutes. j minus square root 3i, right? J minus root 3i. So let me ask whether up to this it is fine, whether you are getting the k unit vector like this. Okay, so if it k is fine, let us check now. So h is in the direction of k. So and k unit vector is, let me think. So k unit vector you are getting is half I cap plus root 3 by 2 j cap. And we have e, and so we have expression like this, right? So I think this one is also fine. Is k cross h by v epsilon. So we have 1 by v epsilon, and I have taken out the half, 1 by 2 I k plus root 3 j k cross h k k. The whole expression is 1 minus sign you missed. So minus sign. You mean, I think this one. Curl of h is divided by t. So I omega. If there is a minus sign, then it will be like minus of this. Curl of h is I create. Okay, so there will be a minus sign here, let's say. I think it's from this, you will get a minus sign. But I think that, okay, 1 by 2 v epsilon I root 3 jk cross k. So I k will give minus j plus root 3 jk will give I k. The minus sign will be in whole part. So you will get root 3 I k. Sorry, jk minus root 3 I k. Okay. Okay. Okay, then I think you are correct. I have missed one minus sign, so answer will be A, not C. Sorry for the mistake. So this will be IK plus minus root 3. Sorry, JK minus root 3 IK. Okay, so thanks for the clarification. I don't know how I got missed this minus sign. So this will be there. Okay, so let's move to our next problem. Okay, so electric field is given and you need to find out what is the average value of the Poynting vector. And the expression is this. And so it's quite straightforward. You know what is the relation S. It is half epsilon naught A naught square C. Half epsilon naught you will get 8.85 into 10 to the minus 12. E naught is the magnitude of this amplitude, which is root 2. Root 2 square will 2 and 3 into 10 to the power 8. This will cancel and you will get around 27 into 10 to the minus 4. Option B. This, the only the power is different for all these. If you look at the answer, only you need to see the power. So it's minus 10 to the minus 4. Okay. Okay. So let us see question number 8. So for first part, there is a consider a long straight cylindrical wire of electrical conductivity sigma and radius A carrying a uniform axial current of density J. For this, calculate the magnitude and direction of the Poynting vector at the surface of the wire. Okay, so you have a conducting wire, like it can be metal. So you need to find out what is the Poynting vector at the surface of this conductor. So for that, you need the electric field and the magnetic field. So if you consider the conductor, so conductor it satisfies J is sigma I, right? So you can take is J by sigma. So this is inside the conductor, it satisfies the Ohm's law. But if you look at the continuity at the surface, whatever what is the electric field is closer to the surface, it will be also at the surface, right? For the continuity equation to be valid. So that means we can take this is the electric field at just outside the surface or at the surface. So J is J by sigma, and for the magnetic field, this is B is mu naught I by 2 pi r, right? If you take the Ampere's law, uh, like BDL is mu naught I enclosed, or B is mu naught I by 2 pi a pi cap. Or in terms of J, if you want to write it, so I is J pi a square. So pi a. This is the magnetic field at a point outside the conductor or the electrical conductor. So, and to satisfy the continuity, you can also take this is also at the surface. Just at the surface, this is satisfying mu naught J by 2. So that means S is E cross H, or in terms of B, E cross B by mu naught. We know E, it is J by sigma, and B is mu naught J by 2 pi k. So if we consider that electric current is moving in the z direction, so you can write this is Jz cap. So mu naught will cancel, and you have J square A by, I think, 1. sigma z z cross 5 will give minus r cube. Up to this, is this fine? It is okay. Then let us see. So this is at the surface of the Poynting vector. We have the magnitude and the direction of the Poynting vector. For the B part. So for B part, it is telling consider a thick conducting slab of conductivity sigma exposed to a plane electromagnetic wave with peak amplitude A naught and B naught. So you have that conducting material. Now you are exposing it to a plane electromagnetic wave. Calculate the Poynting vector within the slab and calculate the average in time over a wave period. Consider the sigma is very large, so it is a highly conducting material. This condition is also given. So if you recall, whenever you have a conducting material, so there will be absorption. So if you look at the absorbing reason of, so we are now considering it is metals are mostly absorbing. But if you change the frequency region to microwave, so metals are not that absorbing. But for now, we are considering that metals are absorbing here. So for whenever we have a absorbing material, so the wave vector you can write it as it will also have a imaginary part. So in addition to the real part, we will have a imaginary part, which will attenuate the electromagnetic wave inside the conducting material. And if we take that the electromagnetic wave is propagating along the z direction, so you can write it as z or whatever unit vector you want to take. So for now, let us take it is in z direction. And if you recall for the metal, you can write it as omega square root ln mu by 2 square root all plus sigma omega epsilon squared plus 1. It is quite similar to the alpha, only the sign inside the square root is different. Here we have minus. And it's also given sigma is much greater than omega epsilon. So we can take, this is the dominating factor in the square root. So that means you can write it as omega and this will give square root sigma by omega epsilon. Similarly, for alpha also you can make the approximation and you will get the same value because we are neglecting this plus and minus, also this one because sigma is very large. So for this case we have alpha and beta value are the same and this will be square root sigma omega mu naught by 2. This so for this alpha is beta, this is square root sigma omega mu naught by 2. So let us calculate the Poynting vector now. Electric field inside a conductor, if you recall, this is E0 R. There will be exponentially decaying factor, which is beta Z for our case, because beta is the imaginary part. and there will be a propagating wave which is I alpha z minus omega t. That means you can write HRT. This will be 1 by omega mu naught A cross C. So omega mu naught K is alpha plus I beta ZK cross E0. Alpha is equal to beta, so that means we can take out alpha and we have 1 plus I ZK cross E0 and beta Z. This is the expression for A we have. So if you simplify it, 1 plus I you can this you can write it as e to power. I think we have to multiply root 2. So here we can what you can do, you can divide a root 2 here and multiply root 2. So that means it will be 1 by root 2 plus I by root 2, which is nothing but e to power I pi by 4, right? So that means we have to multiply root 2 also here. Cos E. This is the H we have. Now S is E cross H, which will be alpha. We can do value of alpha is square root sigma omega mu naught by root 2. E to power I pi by 4 E cross Z plus E. This is the vector identity. This will give Z E dot E minus E dot J. This is 0. So we have sigma omega mu naught E to power I by 4 E square Z2. Okay. So this is the Poynting vector that we have. Let me write it again. So is the steps are clear? Let me know if you are getting any other answer. This is the S that we'll get. For the average over time, we can use the formula. So whenever the simplest expression is given, like E is written in terms of cos and sine. For that case, you can directly use half epsilon naught C E naught square. But whenever you are seeing a phase factor, so I think it's better if you start from half real E star cross H. Okay. So sigma omega mu naught real part of V star cross H is or I think correct. I think this is so this will give 1/2 A star E that is mod of A square and there will be a set which is nothing but what we have seen here. Okay. You can directly use this also instead of putting E and H then. And real part of this is cos pi by 4. This will give cos pi by 4 E square Z cube. The sine part won't be there because this is in the imaginary part. So we will get a 1 by root 2. So now we have 1 by 2 root 2 square root sigma omega mu naught E square. This will give A naught square. Mod of A square will give A naught square e to our 2 beta z. Right? This part, when you take the mod, it will cancel with the complex conjugate part. So you have e to the minus 2 beta z, zk. So this is the average value of Poynting vector inside this conductive slab. So is this correct? I mean, whether the steps are clear to you. I hope the steps are, I'm not wrong this time, I think. The steps are right. Dinakar and Sisti, is it clear? The steps are, is it clear to you? If you want, then I will let you give some time to go through the steps. Okay. So what I have done is, so you know that for a conducting medium, the key is, it will also have a real part and a imaginary part. So real part, the physical significance, it's like, it corresponds to the propagating wave vector. So whatever the wave is propagating inside the medium correspond to that wave vector or the propagation vector. And beta is the term that we use to indicate the absorption inside a medium. Okay. So whenever you are conducting medium, you can write K is alpha plus I beta. And what I am taking, let's say the wave is propagating along the Z direction. Okay. So this is what we are taking. We don't know what is the orientation of electric field, but we are taking that it's, let's say, it's propagating along the Z direction. And most of the cases you will see in most of they always take Z as a propagation direction. But you can also take other direction and the values will be same. So for now it is, let's say it is Z direction. And this expression, this you have already seen in the class. So this is detailedly derived in the class. This is for the real part. The expression for alpha is like this and the expression for beta is like this. And it also given is that the alpha, the sigma is much, much greater. So that means when you have square root 1 plus sigma by omega epsilon square, so this factor will dominate over 1, right? So this condition is nothing but sigma by omega epsilon naught is much greater than 1. So that is why I have neglected this, and square root of this square will give sigma by omega epsilon. And there is a half here also, and we are also neglecting this plus or minus 1 because it's negligible. So this half will give square root of sigma by omega epsilon. And because and for this you will see alpha and beta, they are equal because only the difference is plus 1 and minus 1, which we are neglecting here. So alpha and beta are same, and we are getting root over of sigma omega mu naught by 2. Up to here, is this okay? If not, let me know. Okay. So after that, what we have done, this we have seen in the class. That is, if you put the value of k, so the general expression for a plane wave, like it is a naught e to power I k dot r minus omega t. But when k is imaginary, like it is having alpha plus I beta, so that means this you can write it as e naught e to power I beta will give a minus beta z, and the usual expression of e to power alpha r minus omega t. So this is the expression for the electric field inside a conducting medium. We know we have taken the electric field. In the next step, we have calculated what is the magnetic field so that we can get the Poynting vector. Okay. Uh, this expression, I hope this is we have seen earlier also, k cross e by omega mu naught. So in the next step, what I have done, I have just put the value of k, which is alpha plus I beta z k, and the value of e. Okay. In the next step, what I have done to simplify it further so that I can get a real part. So this is nothing but a phase factor. So to simplify, to write it in terms of some exponential so that you can combine it with this propagating vector, and we'll get finally we'll get the real part and the imaginary part. So that is why I have simplified. I have multiplied root 2 and divided by root 2. So 1 by root 2 and plus I by root 2. So this is nothing but cos pi by 4 plus I sin pi by 4, which is e to power I pi by 4. So this is the phase factor we have simplified. In the next step, I have just put the value of this h. Sorry, I have calculated what is the simplified expression for the h. So this is the final we will get. Is this clear up to this? Okay. After that, what I have done, so Poynting vector is nothing but a cross of E cross H. So we know E, this we have taken, and H, this is we have calculated. So I have just put it here. So E cross H, E will, we are writing E as a, we are keeping it is at the same. And for the H part, there is a Z cross E. So this is what I have write it here. So I have taken out whatever the constant is there, and I have just combined the cross product in towards the uh, uh, extreme side. Okay, so this is E cross Z cross E, and this is the vector identity when you have a 3 cross product. So you can write it like this. This part will be 0 because the propagation vector is perpendicular to the the plane at which the electric field is oscillating. So E cross Z, which is the propagation vector, is 0. So we are left with ZK E dot. So that means we'll get the Poynting vector as this expression. Okay. So is this fine up to this? What I've done next is that I have just used what is the original formula for the Poynting vector. So this is the original formula. You will get half C epsilon naught A square if I'm not wrong. So this you will get it from here. Okay. So this I have used the original formula, and what I've done, I have just put the value of so instead of calculating again, what you can do, you just use this expression here. Okay, so what I mean is you can directly write S is real by 2 and E cross S is root sigma by omega mu naught e to power I pi by 4 E square Z. Okay, rest is modest. Rest is what I have done is I've just filter out what is the real part of this expression. These are all real. Only we need to take the real part of e to power I pi by 4, which is cos pi by 4. So this I put it here, and rest is I think you can easily get it. Is this fine, Srishti? Okay, so let us move to our next part. Next part, there is a approximation. Let's say sigma is infinity. Then what will be the value of every corresponding vector everywhere in the space? So this is quite conceptual. Can you let me know the answer? What will be the Poynting vector given the average value of Poynting vector is this, and you are taking sigma is tending to infinity. So when sigma is infinity, you can see there is a. So what is the dependency of S with sigma? There is a root over of sigma here, and there is a 2 beta here, which is related to the sigma. Because if you see here, beta is related to sigma, square root of sigma. So that means S is this square root sigma e to power minus 2 beta z. And when sigma tends to infinity, this exponential factor will lower the value of S. So that means it will tends to 0. So that means whatever wave is incidentating, it will get totally reflected because it's a highly conducting medium. Okay. So whatever incident wave is there, this will be totally reflected. And whenever you have a situation like this, that is the two oppositely propagating wave carrying same energy. So this is nothing but the standing wave, and they don't carry any energy. So that means S will be 0 everywhere. Okay. They will destructively interfere and S will be 0. Okay. Let us move to our next problem. So for question number 9, uh, there is a for a constant uniform electric and magnetic field. E is E naught, B is B naught. So these are constant electromagnetic field. It is possible to choose a Lorentz curve such that the scalar potential and the vector potential A are given by. Okay, so the question is asking whenever you have a constant electromagnetic wave, uh, in these four options, which one of these following we can take so that it will satisfy the Lorentz gauss condition? So for this, let us see what are the options and what is the value given is A naught. Let's say we are taking the Cartesian coordinate so that we can find out the cross and the dot product easily. This A naught. This is the A naught vector. This is the B naught. And if you recall the Lorentz gauss condition, it is given by divergence of A should be minus 1 by c square dou phi by dou t. Here there is a B0 cross R is there that we need to calculate E dot R and E dot E T. So B0 cross R, it's quite easy for the Cartesian coordinate, and I'm just rightly writing what will be the answer. Z minus y, x k minus z minus x, y k plus y minus x k k or z k. This is B0 cross R. So that means if you take the divergence of A, then this is A we are considering. This will be half of divergence of B0 cross R, which will be, if you take the divergence of this is 0, right? Which is, according to Lorentz gauss, it is 1 by c square dou phi by dou t. So that means if you take the potential is half of B naught cross R, the dou phi by divergence of A should be 0 and the dou phi by dou t, it should be 0. So that means phi can be a constant or it can be a 0 value. Okay. So let us check the options. For option A, when A is half of B0 cross R, it's given phi is 0, which is correct, right? So if you take A is half of B0 cross R, and if you check whether it is satisfying the and phi is 0, and if you check these two condition and check whether it is satisfying the Lorentz code, it does satisfy it. So that means this is the answer. For B option, it's given it is the same vector potential, but phi is minus E0 R vector, which is not a constant value or a 0 value. So this can't be true. For option C, it's given A is 0 and phi is E0 dot R. So let us check it. So option C. So when A is 0, that means divergence of A is 0, right? That means dou phi by dou t should be 0. So when A is 0, phi should be a constant or can be a 0 value, which is not true. For C option, it's given they are taking phi is E0 R. It's not a constant, it's a function of X, Y, and Z. So that is why option C is also not correct. For D also, you can check it by taking, let's say, if phi is 0, that means dou phi by dou t is 0. Or let's start from A is given is minus E0 t So that means rho phi by rho t is C E0 C square t. E0 t, not t. So this will give phi is, so calculate phi here. So this will be 3 by 2 E naught. Approximately this will be 3 by 2 E naught C square T square. And it's given phi is 0. So that means it's contradicting. So answer will be option A. Okay. So is this clear? Can I move to the next question? Next question is quite easy. So I think I will let you to find out. Answer for this will be option B. Just check it. It's directly formula based. So it's better if I skip it. Let us see our next problem. For the 11th question, there is a plane electromagnetic wave which is propagating in a lossless dielectric, and the electric field it is given by E x y z t is E0 xk plus azk exponential ik0 minus ct plus x plus root 3z. Okay, so this is the electric field expression that you have. See the speed of light E0, A and K0 are the constant. And xk by zk are the unit vector along the x and z axis. So for this, calculate what is the relative dielectric constant of the medium and what is the value for the constant A. If you look at the option epsilon r is same, uh, you can scale, you can just check the value for amplitude. But it's better if you check how you can get the value of 4 so that you can check whether this is actually the answer or not, and you can calculate what is the value of it. So calculate it, first calculate it, and let me know whether you are getting the answer or not. If not, I will show you the steps. Use the Maxwell's equation in a lossless dielectric. What is the expression? How you can simplify it so that you can get the amplitude and the relative dielectric constant. Uh, Dinakar, I think you have raised. Let me allow your mic. Yes, you can speak now, I think.
Is it option A?
Let me check. Yes, it's
Because
option A.
because the propagation vector and it is being a dot product with the amplitude of electric field, it would produce zero because of orthogonality property.
Yes. Yes, you
Uh,
got the what is the question is asking about. So K dot E should be 0. So first you need to find out K, then take the dot product. So your answer is correct. Good. So you will whether you are getting epsilon r is 4.
that I don't know, ma'am.
Okay. So for epsilon r, so relative permittivity, it is related to the refractive index, right? So what you have K, you know omega. So what you can do, you can calculate the V and
Hmm.
you can relate it to the refractive index because refractive index is nothing but C by V, right?
Yes, yes. Okay. The
Ah,
K is known already. So with that,
yeah,
we would be able to find V and then refractive index. Then the refractive index has the relation with the dielectric constant, which is root of something. N is equal to
ah,
root of epsilon.
hmm, sorry. Hmm. This is epsilon mu naught. For a non-magnetic material, you can take epsilon. It is square root of epsilon r. Okay.
Yes.
So let me just briefly show the steps so that you won't miss out any intermediate step. So K, I think you will get. So this is Kx, this is Kz. So this will be K0 x k plus root 3 z cap. So that means mod of K, this will get 2K0. And omega is the coefficient of T, which is K0C. So omega is K0C. So that means V is omega by K, which is K0C by 2K0. So C by 2. So that means C by B, this is half, which is nothing, sorry, C by B will be 2, which is nothing but the refractive index. So refractive index is square root epsilon r, so epsilon r is 4. So this is how you can get the relative permittivity. For A, is Dinakar said, you just need to, so divergence of E is 0, so K dot E is 0. You know K, you know the electric field expression. So briefly, it will give 1 plus root. Okay, let me show in detail so that will be easier. So K, I think it's here, is already this one. So when you take the dot product, escape with escape will give 1 and root 3 with A will give root 3A. This is 0. So A is minus 1 by root. Okay, so let us see our next problem. So there is a plane electromagnetic wave which is traveling along the positive z direction. The maximum electric field along the x direction is it is 10 volt per meter. So for this, find out what is the approximate maximum value for power per unit area and the magnetic field induction, which is P. So in vacuum, this is this is E max, nothing but the maximum value of E, which is amplitude of electric field, which is E0. So B0, it is related to E0 by E0 by C. E0 is given 10 and this is 3 into 10 to the power 8. And this will give 3.3 into 10 to the minus 8. So you have two options for 3.3. It is say power. So power per unit area, average power per unit area is I, which is half C epsilon naught E naught square. This is half C 10 to the power 8. And just put the values. This will be around 0.132. Okay, so let us see our next problem. I would like you to first try it and let me know the answer because it's quite straightforward. There is a, if the electric field and magnetic fields are unchanged when the potential A changes according to A goes to A plus R K, R goes where R is not A R. What is the change in scalar potential so that the electric field won't change? So you want to calculate what is the final expression for phi prime. A prime given A prime is this.
Ma'am, is it option C?
Yes, it's option C. Okay. So it's good that you are getting the answer. So I think you must have used A to make it unchanged. The transformations would be this, and you must have equated to RK. This you can write it as 2 lambda by 2 RK is RK. So that means lambda is R or some R plus some constant. So for phi prime, it should be phi minus dou lambda by dou t. And if you take the time derivative, so this is dou r by dou t. So that means option C. Okay, good. Let us see whether you are able to recall the concept from the previous classes. So this I think we have seen before also, and it's also related to the content that has been taught in this way. It's based on the boundary condition. Suppose the YZ plane forms a chargeless boundary between the two media of permittivity epsilon width and epsilon depth. It's given the ratio is 1:2. If the uniform electric field on the left, if E left is C I K plus J K plus K, that is the constant. So then what will be the expression for E right? So if the light or the electromagnetic wave is traveling from left to right, what will be the expression when you get to the right? Just recall the boundary condition. I think you will get the answer.
Ma'am, is it B? Option B?
Option B. Yes, it's correct. Okay. So good. So always remember one of the boundary condition. I think you can easily guess what is the boundary condition for other. Like for the electric case, the parallel component is continuous and the perpendicular component is discontinuous and it is given by the surface charge. But it is quite opposite to the magnetic field case. For magnetic field, it is the perpendicular component which is continuous and the parallel component has discontinuity which is the surface current and it is given by K plus C. But for now, it is not asking about the magnetic field. So for electric field, E parallel should be same. It's given this is the YZ plane. So parallel component should be Y and Z. For the plane, it is the parallel component and perpendicular component is the I cap. So that means for the right case, the parallel component for the right would be the same as the parallel component on the left, which is JK plus KK into C. And for the uh, perpendicular component, you can take use of the perpendicular. Because sigma f is not given, so this you can take 0. So this is epsilon left, E1 left, and epsilon right, E2 right. This is perpendicular, so E2 will be E1 by E2, E1. And E1 by E2 is given 1 is to 2. So this is C by 2. Option B. Okay, let us move to our next problem. An electromagnetic plane wave is propagating with an intensity is given by 10 to the 5 watt per meter square. In a medium with epsilon is 3 epsilon. This is the medium permittivity. And mu is mu naught. It's a non-magnetic medium. Amplitude of the electric field inside the medium is. Intensity is given, so that means you can relate it with uh, so for a medium, don't take epsilon naught. It is epsilon, and C will be replaced by V square. This is given 5. E square is epsilon is given. It is 3 epsilon naught, and V for V, what you can do, you can write in terms of. So V is nothing but 1 by square root epsilon. So this will be, so that means E square will be 2y square root mu by epsilon. Just put the value of epsilon naught, which is 8.85 and mu naught is 4.10 This will give, so I'm skipping the calculation part. This will give, E will get 6.6 into 10 to the 3. Okay, so let us see our 16th question. Given electric field of a plane wave in a conducting medium, it's given by ZT is I cap E0 equal Z by 3 cos Z minus root 3 minus omega t. What is the phase difference between the magnetic field and the electric field? So in a conducting medium, as I said during our introduction, so the phase, they are not in phase. So if you see vacuum, they will be in phase. But when you consider a conductor, there will be lagging behind E and B. So for this case, you need to calculate what is the phase difference. Okay. So for this, what you can do, phase is nothing but the coefficient of e to power. Sorry, let me solve it. So phase is not whenever you have a electric field like this. So this is the phase kr minus omega t. So what you can do for to find out the phase, what you can do, you can just write in terms of the complex part. Don't take the real part. So this is nothing but the real part of the exponential. So we can always write it as a the exponential part also. And whenever you are calculating the Poynting vector or the actual measurable quantity, for that case we take the real part. But for our question, let us take this is E naught I k e to power z by 3 exponential I z minus root 3 minus omega t. We have E, we can calculate P. K cross E by omega. K is easy to find out. There is a real part, there is an imaginary part here. So that means K is Kk by root 3A plus Ikk by 3. So Kk by 3A root 3 plus I. So to write it in terms of exponentials, similarly, in one of the question, I have multiplied 1 by root 2 and divided by 1 by root 2. For this case also, you can see root 3 is there. So you can multiply 2, sorry, divided by 2 and multiply 2 here. And this is e to power I 5 by 6. Okay, so that means we have ds 2 by 3a is 0 e to power z by 3 e to power I pi by 6 jk. So this you can write it as, so I'm just taking it a constant which is b0 e to power minus z by 3 e to power I z minus root 3 minus omega t plus pi by 6. So I have just taken this one to inside. And if we compare it with the phase of this electric field, only the additional factor is pi by 6. So that means the phase difference is pi by 6. Okay. So we'll see the rest of the problem in the next class. So in next class will be our last live section for this course. So I will try to cover, revise the concept. I will try to take problems that will revise the concept starting from week 1 within this 2 hours course. So please try to attend that the live session because it will be only the only will be only solving the problems and will be calculating the solution. Okay. For now, Dinakar, when if do you have any doubt? Let me clarify it first because I think we don't have much time. So we'll
Yeah,
see
so
the okay,
yeah, as of now, I don't have any doubts regarding this problem. So, yeah, you should proceed.
okay, okay. So thank you for joining the section. Let us meet on. I think we'll get the notification. We'll have class on after 2. Let's wait for the official notification. Please try to attend that. We'll try to solve few more problems. For now, let us stop. So thank you for joining the section. Goodbye, everyone.
Thank you.
Thank you.